Today we're going to be looking at function families, and you have to be able to recognize the different typical families of functions from their graphs as well as from tables. So we're just going to go through, I believe, 11 of the function families you have to be able to recognize and talk about their characteristics and easy ways to identify which function belongs to which family. So the first one we're going to look at should seem pretty familiar. Linear functions are something you've been working with since Algebra 1, if not before then. Some of the characteristics about linear functions are that they are a straight line on a graph and that they have a constant rate of change. We also call this the slope. So up 3 over 1, being able to find the rate of change from a graph. For linear functions, it's the same no matter where you look on the graph. And then a parent function is just the most basic form of the function family. So this is the most basic linear function you can get. It's just a regular y equals x. A lot of times we'll have students put y equals mx plus b, which is what you learn for slope-intercept form, but this is still the most basic version of a linear equation. So when I ask you for the parent function of a linear function family, this is what I want you to write down. The next graph that we're going to look at is a quadratic function, and it has a very typical U-shape parabola. This should feel pretty familiar to you. We worked with quadratics previously, and this quadratic has a minimum value right here, but you could also have a quadratic function that goes this way, and then that would be an example of one that has a maximum. It's still that U shape, it's just whether it's an upside down or right side up. And then the most basic quadratic equation you could have is y equals x squared. Next, we have a cubic function, and a cubic function typically has 2 bumps, and it has a maximum and a minimum value. Now, this is a very exaggerated cubic function. Sometimes you'll even see cubic functions that look like almost like this. But it still has these 2 smaller bumps right there, and so that's the characteristics. That's one of the characteristics you can identify of a cubic function. And then obviously, a cubic function has y equals x cubed as its parent equation. After the cubic function, we're just going to classify anything with larger than a 3 in the exponent as a higher polynomial. Technically, a linear, quadratic, and cubic function are all polynomials as well, but we could obviously continue this trend for forever, and so the most important ones I want you to be able to recognize are linear, quadratic, and cubic, and then past that we can just call them higher polynomial functions. And so some of the characteristics of those are that they would have multiple bumps, and then they have minima, which is just the plural for minimum, so there's more than one minimum points, and then a maxima as well. And then a parent function for this, you guys could write down y equals, and then just write a couple of these, and I'll know what you're talking about. You're just identifying that these are the most basic forms of each of the higher polynomial functions. Now we're going to get into some trickier ones that you might not be as familiar with. So the first thing that we have is a radical function. And I like to joke and say that if you want to remember that this is a radical equation, you can view it as a wave, and then you can pretend there is a little surfer dude who rides on the wave, and he's yelling, "Radical, dude." So whatever you need to remember that this is a radical equation, that's fine. It's increasing at a decreasing rate, and one big important part that separates this radical equation from one that you'll see later on is that it has a stopping point right here. So it doesn't continue going down. It just actually stops or starts right here. And then radical is another name for a root, and so the most basic radical function that you can come up with is y equals square root of x, and so that would be the parent function for radical function families. The next one we have here is exponential function, or is an exponential function family, and the typical characteristic is that it increases at an increasing rate. When I try to get students to remember this, I always say that I would like my money to increase exponentially, because it would be ideal if, even if I start off with a little bit of money, that it would just grow exponentially. And then y equals b to the x is the parent function, and here it might be important to know that b is a number. So you could have, for example, y equals 2 to the x. You could have y equals 1.5 to the x. And then one you'll see a lot is for true exponential growth would be y equals e to the x, where e is an important number called Euler's number that shows up a lot with interest rates and money and in other places in nature. And so these would all be examples of exponential equations, but you can just write this down as the most basic parent function. Next, we have a logarithmic equation, and this is the one I wanted to differentiate between radical, because obviously this one kind of looks like a wave as well, but there are some other important characteristics about logarithmic equations that are easy to identify it and separate it from a radical equation. So a logarithmic function family, it always crosses the x-axis, and then it has a vertical asymptote. Now, asymptote might not be a word you've heard in a while. An asymptote is a line that your graph approaches but never touches. And so here is where the vertical asymptote is on this graph, which means that your logarithmic function, if you followed it, it's just going to keep going down, 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 down forever and ever. It's never actually going to touch this vertical line. And so that's one of the characteristics that separates the logarithmic from a radical, is that this will continue to go down forever, whereas our radical function stopped. And then there are two parent functions you could write down for the logarithmic function family. This is what's called a common log, because it actually has just the word log in it. And then when you have ln, this is a natural log. So you could write down either of those as the parent function, or you could write down both of them. That's up to you. So a natural log or a common log. We have a couple more coming up. So rational function family. So a rational function is one where the parent function has the variable in the denominator of a fraction or in the bottom of a fraction. So this is the most basic parent function you can have for a rational equation. And a rational equation usually has vertical or horizontal asymptotes. So those asymptotes, again, those lines that your graph approaches but never touches, that would be a big characteristic to look for identifying the rational function family. This one tends to be pretty easy for students. This is an absolute value graph. These absolute value symbols should pop up in your memory a little bit. Absolute value symbols represent the displacement of this number from 0, if I'm getting real fancy. But what my students most often remember the absolute value symbols for doing is just changing whatever the number in here is to positive. So even if this was like the absolute value of -2 is just 2, and the absolute value of 2 is 2. So no matter what number is inside of absolute value symbols, the answer is always going to be positive. And the easiest way to represent an absolute value or recognize an absolute value graph is from its typical V shape. And so it doesn't have to look completely like this. It could be upside down, it could be really skinny, but as long as it makes that V shape, then you can identify that as an absolute value graph. Piecewise defined function, sometimes shortened to just calling it a piecewise function, is most easily identified for the fact that it's broken into pieces. And that's true for both the example that I have here as well as the graph itself. There is no typical parent function for a piecewise graph because it can just be made up of anything, but it usually will have two or more pieces that are identified in the function. So this is what this graph looks like. You could also have a piecewise function that did something like this. It doesn't actually have to be separated. So I could have a graph that does this and then goes up and then goes down and then goes flat again. Each of these would be an example of a piecewise function because 1, 2, 3, 4 separate pieces. They don't form a smooth curve or anything like that. So they don't necessarily have to be separated at a point, but they could be in different chunky pieces on the graph. And our last One we have to be able to identify from a graph we've actually already talked about a little bit. Non-functions are just relations, and a characteristic of your non-functions we talked about in our previous notes is that it fails the vertical line test. So if you can draw a vertical line through it and it hits 2 or more points on that line, this would be an example of a non-function. And then this is, again, just an example equation because non-functions could come in any form in the equation. So this is just one example.